For more than 3 centuries, serious arithmetic could mean moving metal instead of electrons. Inside polished boxes and cast iron cases, carries, borrows, products, and quotients had to be made physical, and every jammed tooth could turn confidence into fiction. This field is hand-operated mechanical calculators before handheld electronics took over. No electric motors, no punched card computers, and no slide rules. The machine must accept numbers, perform arithmetic through mechanism, and show a reusable numerical result. The obvious temptation is to reward the first machine that worked. But first is not the same as greatest. A laboratory marvel can change history while remaining too fragile, slow, expensive, or awkward for ordinary calculation. So the ranking uses 6 tests: range of operations, speed, reliability, ease of use, portability, and historical impact. The winner does not need every category, but it must combine more of them than any rival. Addition is mechanically friendly. Turn one wheel and carry a 10 into the next column. Subtraction reverses or complements that process. Multiplication and division are where machines begin, demanding either repeated motions or much cleverer gearing. Sum matters because early calculators were furniture adjacent. A machine could be brilliant on an office desk and still be useless to a surveyor, engineer, or navigator who needed arithmetic somewhere inconvenient. Speed also depends on the operator. Some machines reward practiced fingers. Others automate a difficult step but demand levers, carriage shifts, and careful bookkeeping. Mechanical calculation was often a partnership between ingenious hardware and a very awake human. The 6 finalists span from the 17th century to the electronic cliff edge. Each solved a real problem, and each exposed the next one. The winner will be the machine that turned those accumulated lessons into the strongest complete package. And there is a final complication. The most impressive mechanism may not be the fastest. Greatness here means the machine a skilled person could trust, carry, understand, and actually use, not merely admire behind glass. At number 6 is the Pascaline. Blaise Pascal began designing it in 1642, creating what Museo Galileo describes as the first fully mechanical calculator. Its numbered wheels could add and subtract, while an internal carry mechanism moved value between decimal places. That carry was the breakthrough. Arithmetic no longer lived only in written procedure. Part of it had become a machine state. Multiplication and division were possible through more involved repeated processes, but they were not the Pascaline's natural strength. Its limitation was brutally practical. Cuts were costly and difficult to manufacture. Demand was weak, and only about 20 machines were built. The Pascaline proved the idea, but it did not yet make mechanical calculation an everyday tool. At number 5 is Leibniz's stepped reckoner. In 1673, Gottfried Wilhelm Leibniz presented the first true 4-function calculator, using a stepped drum whose uneven teeth could represent any digit from 0 to 9 in one revolution. That drum was more than one clever machine. Variations of the principle became a foundation of mechanical calculators for roughly the next 275 years. Few components in computing history can claim that kind of mechanical afterlife. The reckoner could add, subtract, multiply, and divide, pushing the field beyond Pascal's practical emphasis on addition and subtraction. It established the dream of one machine handling the full arithmetic set, but it remained closer to a heroic prototype than a dependable commercial product. Leibniz built versions across decades, and only one survives. Its mechanism became immortal. The machine itself never became ordinary. At number 4 is Thomas de Colmar's arithmometer. Patented in 1820 and refined for decades, it became the first commercially successful calculating machine in the 1860s, an important shift from singular invention to manufactured office equipment. It performed addition, subtraction, multiplication, and division through a mechanism descended from Leibniz's stepped drum. Businesses could buy a machine whose design was understood, serviceable, and repeatable, rather than commissioned as an aristocratic curiosity. The arithmometer's long production life matters. Machines of its family remained in use into the 20th century, proving that mechanical arithmetic could become infrastructure for offices, statistics, insurance, and administration. Yet the office was also its cage. One surviving commercial-scale example weighs more than 10 kilograms. It was a serious instrument for a fixed workplace, not something calculation could casually follow into the field. At number 3 is the comptometer. Invented by Chicago machinist Dorr Felt in the mid-1880s. Instead of setting a number and then turning a crank, the operator entered values directly by pressing keys, arranged in columns. On a comptometer, pressing a key both selected a digit and entered it into the mechanism. Skilled operators could use several fingers across different columns, turning addition into a fast, almost musical physical routine. Felt cultivated business and government customers, and the machines spread internationally. Specialized versions handled fractions and non-decimal currencies. This was not merely an inventor's demonstration. It became a working culture with trained operators. The Model A introduced duplex action, allowing more than one column to add and carry simultaneously. For bulk addition, few hand-operated machines were better, and Smithsonian curators note that the comptometer was especially suited to addition and subtraction. That specialization keeps it at number 3. Multiplication and division required learned procedures rather than one elegant, direct mechanism, and the machine remained desk-bound. It was a superb arithmetic keyboard, but not the most complete calculator. At number 2 is the Millionaire, designed by Swiss engineer Otto Steiger in 1893. Its great trick was direct multiplication. Set a number, select a single-digit multiplier, turn the crank, and the machine formed the product without repeated addition cycles. Most earlier calculators multiplied by adding the same number again and again. The Millionaire used a multiplication body that mechanically selected the required multiple. For its era, watching one crank produce a single-digit product bordered on sorcery with excellent bookkeeping. That made it exceptionally strong for engineers, scientists, and offices doing repeated multiplication. It was not merely faster in a narrow race, it changed which part of the operator's procedure the machine itself could absorb. The build matched the ambition: dense metalwork, substantial controls, and a carriage for positioning decimal places. It looked like a machine that expected a permanent desk and perhaps a respectful amount of reinforced furniture. As a pure multiplication machine, it is the strongest rival in this ranking. The eventual winner cannot match its one-turn direct multiplication. That is an important loss, because elegance should not be awarded by pretending the rival's best feature does not exist, but greatness across the whole field punishes bulk. The Millionaire solved a difficult operation beautifully while remaining expensive, heavy, and fixed in place. The number 1 machine will sacrifice some multiplication speed for something no earlier contender truly achieved: arithmetic mobility. The Curta calculator is the GOAT of hand-operated mechanical calculators before handheld electronics. It did not win by being first or fastest. It won by compressing 4-function calculation, reliability, and genuine portability into one coherent machine. Its creator was Kurt Hertzstark, an Austrian engineer raised inside his family's calculating machine business. Before the Second World War, he had already been developing a compact design based on a modified stepped drum. In 1943, the Nazis arrested Hertzstark and sent him to Buchenwald concentration camp. While imprisoned, he refined the design in his mind and on drawings, preparing a machine he hoped could be built if he survived. That history should not be polished into a convenient invention myth. The achievement emerged under persecution and forced confinement, and the machine's later elegance does not soften the circumstances in which its design was completed. After the war, production was established in Liechtenstein, and the calculator was introduced in 1948. From the outside, it resembled a small pepper grinder. Inside, more than 600 parts coordinated around a compact cylindrical core. Numbers were set with sliders around the body. Turning the top crank added them into the result register. Shifting the carriage changed decimal position. Subtraction used the same machine with the crank lifted into its alternate mode. Multiplication came from repeated addition, and division from repeated subtraction, with the revolution counter keeping track. It was slower than the Millionaire's direct product, but the procedure was systematic, visible, and available wherever the operator could hold the machine steady. The Type I accepted 8-digit entries and displayed an 11-digit result. The larger Type II expanded both capacity and size. Neither needed electricity, a desk, or a trained maintenance department waiting in the next room. The physical contrast is startling. Smithsonian measurements put a cased example at about 12.7 centimeters tall and 5.7 centimeters wide. Earlier 4-function machines occupied desks. This one could travel with its arithmetic intact. That portability found a natural audience in sports car rallying, where crews repeatedly calculated time, speed, and distance. The Curta remained popular with rallyists even after electronic calculators appeared because it was rugged, accurate, and usable on the move. It was also a manufactured product, not a lone prototype. Smithsonian estimates roughly 140,000 were made across the two types. Production ended in November 1970, while sales continued into the early electronic calculator era. The complexity carried a warning. The factory used special tools, and the Computer History Museum notes that owners who dismantled the more than 600-part mechanism generally could not put it back together. Curiosity occasionally met 600 tiny consequences. It was not cheap, automatic, or effortless. Large calculations still demanded disciplined cranking, carriage shifts, and careful reading. A direct multiplication millionaire could beat it at its signature operation, and a practiced comptometer operator could outrun it through columns of addition. Then electronics changed the category itself. Handheld electronic calculators became faster, simpler, and progressively cheaper, replacing the Type I by the early 1970s. The Curta did not lose to a better arrangement of gears. It lost to a new technological world. That ending is exactly why the Curta wins. It gathered 3 centuries of mechanical ideas into the smallest all-mechanical 4-function calculator ever built, then reached mature production just before electronics closed the contest. The field ended with its most complete machine.